Welcome to Lecture 12 of Modeling and Simulation of Physical Systems, in which I shall describe the modeling techniques for the fluid power actuators. With the help of two examples, the hydro-mechanical position servo and pneumatic position servo, I shall illustrate how fluid power actuator system can be used to precisely position a massive load, which is otherwise difficult to attain with the help of electromagnetic actuator system. Our first example is a hydraulic position servo, in which we wish to apply a small input displacement U over here to produce large displacement Z applied to the mass M experiencing an opposing force FL. The mass is connected to a piston in a piston cylinder that is filled with incompressible fluid. The pressure of the fluid across the piston in the cylinder is regulated by the servo valve shown here. Essentially, the servo valve is responsible for routing the fluid flow from this side, from this port over here, and it is also responsible for routing the fluid back from the piston cylinder to the reservoir over here. We are going to relate this pressure difference that is responsible for generating the force on the piston cylinder that is acting and forcing this piston to move leftward and move the mass leftward at a displacement Z. We also have a mechanism of feedback that is in the form of a mechanical lever. Note that the servo valve as shown here is not a servo valve as such because it is not actuated by a solenoid current. In fact, the control of the fluid inside the servo valve is provided by the spool, the displacement of the spool, and the displacement variable is X. And we have also marked the length parameters A and B, where A is the distance between the point at which the input displacement U is applied and the point in which the spool is connected to the mechanical lever. And B is the distance from this point, the point of contact between the spool and the mechanical lever, to the point where the piston is connected to the mechanical lever. In this problem, we are going to relate our input, which is the displacement U, with the output displacement Z or Z, and also with FL. FL is another input to the system, and we are going to relate the input displacement U with output Z as well as FL. Sorry, FL is the output so let me correct that. So we are going to relate Z. So let me write it down over here. So relate Z with U and FL. So we're going to relate the output Z with the input U and as well as the other input FL. So first of all, we shall try to understand how does this mechanical lever work to provide a mechanical feedback to the servo valve. Essentially, if we want to apply the input displacement U as shown here, we want a corresponding output Z that is directly transferred to the displacement of the mass through the piston inside the cylinder. In an ideal scenario, the displacement of the spool X is equal to 0. It is acting like a pivot, so that a small input displacement U causes this lever to rotate about this point and result in a large displacement Z applied to the mass. And Z and U, we would like to have them related in the form of a proportionality relationship, so that Z is some gains times the input displacement U. And we want this gain to be as high as possible so that small change, small input displacement leads to a large output displacement Z. However, the displacement Z is a consequence of the force applied to the piston over here. And that force must have come about due to the differential pressure exerted by the fluid on the piston. Hence, we can say that as, in fact, we should say that Z increases as a consequence of a differential pressure applied by the fluid on the piston, which means that we inject more fluid over here on this side of the piston cylinder, that is to the right of the piston, and we are forcing fluid to flow back from the left hand side of the cylinder back to the reservoir. However, when x equals to 0, which is the default state of the servo valve, it allows no fluid flow. The simplified internals of the servo valve as shown here can clearly indicate that there is no possibility of the fluid flow because the ports are completely blocked. Therefore, there is no fluid that can flow from this side over here, or it maps to the point over here, over to this side A. That is, there is no fluid that can possibly enter the piston cylinder, and likewise there is no fluid that can possibly leave the cylinder and go back to the reservoir. So the flow is completely blocked, and that's not possible. This means that if we want to have some displacement Z applied to the mass, there is going to be x greater than 0. X greater than 0 means that we are displacing this spool rightward as shown here with a displacement x, and that is going to unblock the ports, which enables the fluid to flow from this point, the input delta, where the pressure is delta PS, all the way to to the output port A, and that's where it will enter the piston cylinder. And it also enables some fluid to leave from port B back to the reservoir. The fluid flow is a laminar. We can relate the fluid pressure difference applied across the piston cylinder, that is delta P naught, with the input pressure delta PS, using the fluid resistance expression for the laminar flow. In this case, we're going to subtract delta PS, the input pressure, minus the pressure drop, which comes about due to the fluid resistance. So here R is the fluid resistance. So R is the fluid resistance, and Q naught, this Q naught is the flow rate over here, the flow rate that is associated with the piston cylinder, not at the input. But note that this expression, that the fluid pressure difference across the piston cylinder is equal to delta PS minus RQ naught, is true in case of maximum fluid flow, that is for the maximum value of X when the ports are completely unblocked. Therefore, in general, we can say that only a fraction, small g, of the input fluid pressure delta PS will contribute to the pressure delta P naught applied by the fluid across the piston cylinder. And this fraction is naturally proportional to this displacement x, because the displacement x describes the amount by which we are going to, so this x displacement regulates the fluid flow rate as well as the amount of fluid pressure that is appearing across the piston cylinder. Therefore, the first equation, the modeling equation, is delta P naught equals to that fraction G times delta PS minus RQ naught, and this G is proportional to X, so we can say that G is C times X, where C is some constant. So the complete expression will be C delta PSX minus RQ naught. And we can write C delta PSX as GPX. So GP is C times delta PS. So this gives us the equation that the fluid pressure difference across the piston cylinder is some constant GPX minus RQ naught. With the remaining fluid modeling equation, we note that the cross-section area of the cylinder is capital A, and we're going to make we're going to utilize some assumptions in writing the expression for the fluid capacitance. So the expression we derived in the last lecture said that Q naught, the flow rate, equals to the rate of change of fluid volume plus volume divided by bulk modulus times the pressure difference delta P naught. And in this case, because the system is hydraulic, so the fluid used is incompressible. That is, the bulk modulus is very, very large. So that means we can consider this term to be very small or negligible, simplifying our expression, which sets Q naught equals to V dot. Because our goal is to relate the output displacement Z with the force FL and the input displacement U, so we need to eliminate this rate of change of volume term V dot. So what is the volume? Let's look at that. The volume of the fluid inside the cylinder. So in this case, if we set the displacement Z naught as defining the lower dead end, the position of the lower dead end of the piston, and we say that the piston has further moved leftward by displacement Z. So the total volume in this case is going to be the cross-section area times the height of the cylinder, which is this Z plus Z naught is the total height of the cylinder that is responsible for pushing this piston leftward over here. And if we take a derivative of the volume, the constant term will be eliminated, Z naught. We're left with A times Z dot. Therefore, the flow rate Q naught, which was equal to V dot, is now A times Z dot. So now we have an equation, equation 2, which contains a Z term, although in the form of Z dot. I'm going to write down the modeling equation for the mechanical part, and that is essentially the piston connected with a mass and with a lever. We're going to make an assumption here that the mass of the piston plus the lever and the mass of the load, all of these masses add to M. In other words, we're saying that the mechanical lever has negligible mass and the piston has a negligible mass compared to the mass of the load M. So these three components can be considered as a single rigid body experiencing a linear displacement Z. And we're also going to make an assumption that there is no other force applied to the piston or the mass or on the mechanical lever. Under these assumptions, what we can do over here is to write down we are going to relate the force or the forces applied to the piston with the pressure. So we're saying that the fluid on the right hand side of the piston is going to exert some force Fa, and the fluid on the left hand side of the piston will exert an opposing force Fb, and the difference of the two forces is equal to area times the pressure difference. And we're going to use this equation to further to write down the equation of motion using Newton's second law of motion, which is that the net force applied by the fluid causing this piston to move this way, which is in the direction of Z, that net force is F A minus FB, which is same as area times delta P naught, minus the opposing force FL, kind of externally applied to the mass, equals to mass times the acceleration, which is Z double dot, under the same assumptions as discussed before. So now if we make a summary of the equations so far, so the first one is the fluid pressure drop equation. The second one relates the flow rate with the rate of change with the velocity of the mass. And the third equation is essentially the Newton's second law of motion, relating the pressure difference and the opposing force Fl with the acceleration of the mass. And these equations can help us relate the output Z with the inputs U and Fl, as long as the displacement X is eliminated. So the only problematic variable over here is X. So remember, X is the displacement of the spool of the servo valve. So that needs to be eliminated, and once that is done, we can conveniently find expression of the output displacement with Fl and U. It is possible to eliminate X by writing it as a linear sum of U and Z. And this is done by formulating a geometry version of this problem, in which we're going to overlay the final pose of the lever onto the initial pose of the mechanical lever, which is perfectly vertical as shown here. And the final pose makes some angle with respect to the initial pose. So once the geometry version of the problem is formulated, we are going to deconstruct this figure into subproblems which can be solved easily. So how do we do this decomposition? Well, we are going to consider the vector version of these displacements U, X, and Z, and we're going to say that this figure on the left hand side can be decomposed as a sum of these two geometrical figures, or set of triangles, put it in a different way. So putting these arrows is just as important over here. So arrows, and this one is on the left hand side, this one is also pointing left. So we're going to say that if you add up these two vector diagrams, you're going to get this one, which is the original geometry problem. And so some of these vectors, as you can see, are zero, such as U double prime, as well as the Z prime is zero. And the other are pointing in the opposite direction, so X prime and X double bar. So when they're added up, we're going to subtract because they're pointing in the opposite direction, so their magnitude are going to be subtracted. And the equivalence says that U is just U prime plus U double prime, and Z is Z prime plus Z double prime. And these U, X, and Z are the magnitudes of these vectors. Then applying the properties of the triangle, or in this case the right angle triangle, there are going to be two right angle triangles. So in this case, this one is the first right angle triangle, and the outer one is another right angle triangle. And also in this case, this is one right angle triangle. In fact, I should say this is one right angle triangle, and this one over here is another right angle triangle. Then the theorem says that the ratio of the corresponding sides of these right angle triangles must be the same. So that gives us these two expressions. X prime over U prime is B over A plus B, where X prime and U prime represents the dimensions of the corresponding bases of the right angle triangle, and these dimensions B and A plus B are the corresponding dimensions of their hypotenuses. And over here again, X double prime and Z the ratio of x double prime to z double prime is a over a plus b by the same principle. So these two expressions are going to give us that required substitution, and they are going to relate x with u and z, which is simply x equals to b over a plus b times u minus a over a plus b times z. That's because, remember, x was x prime minus x double prime, so this expression goes back to x prime over here, and this expression goes back to x double prime, and at the end we have successfully written x. We have expressed x as a linear sum of input and the output displacement. That is going to be our last equation 4. Those 4 equations can conveniently provide us a means to eliminate x and also q naught to give us the final expression. You can consult that from the textbook as well. That is c equals to b prime over a prime times 1 input u minus 1 over ks times the opposing force Fl divided by m over ks d square minus ra square d divided by ks plus 1, where ks is gp times aa prime. And remember, this ks defines the static stiffness of the system, the one that was analyzed in our lecture on electromechanical systems, in which we said that although the system did not contain any spring, yet it was exhibiting some stiffness. That is the static stiffness that comes about due to the opposing force required to cause displacement in the opposing direction. And b prime over a prime defines the static gain of the system. So this was the quantity we wish to try to maximize, and therefore we can say that if b prime over a prime is large, then for small u we can have large z. In fact, it is the opposite. So if b prime over a prime is small, then for small it means that it has to be large. So this, yes, so let me correct myself. So this has to be large so that small displacement at the input leads to large displacement of the mass. As a homework exercise, you can find out the expression for damping ratio and the natural frequency of the systems, and try to match those with those given in the textbook. Our next example is a pneumatic position servo in which the fluid is a compressible fluid such as air or gas. There is a fluid pressure supply where the pressure is delta PS, and the flow of the fluid is controlled by this orifice, and after passing through this orifice the fluid reaches in this part of the valve, from where it has two possible routes. One is that it goes down here into a piston cylinder and try to push this piston forward to the right hand side, in which case this is going to cause displacement on this mass, that is delta Z as shown here. And the other route is that the fluid can possibly escape through the nozzle of the valve, and the amount of fluid that can escape depends upon the spacing delta Y and also the displacement of the mechanical lever delta Y, that is going to increase or decrease the distance between the flapper attached to the mechanical lever and the nozzle over here. So this spacing is important in regulating the flow and maintaining the pressure delta P naught. Assumptions about this system is that the piston is loaded with the pre-compressed spring, right? So we're saying that the springs in this case are pre-compressed, they are already compressed by some displacement Z naught. In other words, if we allow the springs to uncompress, their leftmost terminal will reach somewhere over here, and that will be the equilibrium position of the spring, both the springs in fact. The mechanical lever and the piston are rigid bodies with negligible mass, as was the assumption in the previous case. So this lever and the piston has negligible mass compared to the mass m of the load. And we say that the equivalent stiffness of both the spring is taken as K. So their configuration is such that we are just writing down the equivalent stiffness, that is K, and the mass M and the lever experience forces FL, and those due to and the force due to the pressure difference of the fluid in the piston cylinder connected to the valve, and there is no other force. So the only force or only forces of our interest are the opposing force FL and the force due to the pressure difference, force due to the fluid pressure difference over here. So we can see that as we increase the distance, as we move this lever leftward, it is going to bridge this gap and increase the pressure delta P naught inside the valve, and as a consequence this is going to increase the pressure difference, the fluid pressure difference, which is going to exert the force on the piston, eventually resulting in the application of the force on mass M, causing it to displace by displacement delta Z. So the mechanism is fairly self-explanatory, and we have highlighted our assumptions in great detail. Although this problem is highly nonlinear, we are going to make a linear model by making several assumptions. The first of them being the linearized version of the nonlinear pneumatic valve. So this pneumatic valve over here is essentially nonlinear, but using Taylor series expansion or the expression, there is an expression, it is an expression given in the book, in which we can relate delta P naught, the pressure difference, the fluid pressure difference inside this piston cylinder, that is 0.671 times delta PS minus GP delta Y times R naught Q naught, where R naught is the fluid resistance. And the other parameters, they are constant except delta Y. Right? But we need to make more or further assumptions before a complete linear model is obtained. Those are about the fluid capacitance, parameters such as the bulk modulus and the volume. Again, they are not constant, but we're going to assume that we could possibly approximate the bulk modulus with its mean value V steric and the volume with its mean value V steric respectively. And once those mean values are obtained, then there is a possibility that by substituting these in the expression of the capacitance, we can be in a better shape to write a linear expression for the system. So what is our goal here? We are trying to relate the input displacement, this time acting leftward, causing the output displacement delta Z acting rightward, and this mechanical feedback lever displacement, that is the displacement of the flapper, is delta Y, which is again going to be eliminated when we shall write delta Y as a linear sum of delta U and delta Z. All right, before that we are going to write the expression for the fluid capacitance. The basic expression Q naught volume divided by bulk modulus times the pressure difference delta P naught plus V dot. And the volume of the cylinder, volume of the fluid, is the cross-section area, that is A, times the volume of the fluid that is trapped over here. So effectively A times Z naught plus delta Z. And if we take a well, this Z naught really doesn't matter actually, because we are eventually going to take V derivative, that is A times delta Z derivative, and that is going to be substituted over here, V dot. But what about this the other part of the expression containing only V and beta, that those are actually time varying quantities, and we have approximated them with their or by their mean values V static and B static. So the final expression, flow rate equals V static divided by bulk modulus beta static times delta P naught dot plus A times delta Z dot. Modeling equations for the mechanical subsystem, that includes the mass and the piston, and they're both connected, representing a rigid body construction. We're going to say that this this combination of piston plus load mass experiences force due to the fluid, that is delta P naught times the area, as seen before in the previous example, and experiences imposing force FL, and also experience force due to the spring. So remember, in this case we do have a spring. It is in fact a pre-compressed spring, so I have to be a bit careful in writing its expression Fs. So we are going to apply Newton's second law of motion and say that F minus Fs minus Fl equals to m times delta Z double dot. The Fs, so this is the force in the direction of motion, so delta P naught times A, fairly straightforward, minus FL, and minus Fs. So minus Fs has been taken over here. So this is K times delta Z plus Z dot. We have to understand this spring force in a more detail. So over here I have described the spring force with the help of its free body diagram. So remember, one end of the spring, the right end of the spring, is fixed. The spring does not protrude this this piston cylinder over here. So this end of the spring is fixed. That's over here. And the other end of the spring is displaced as the piston is displaced. So we know that the piston has been displaced on the right hand side. So the left end of the spring, which is attached to the piston, also displaced, and the displacement variable, and how much is the displacement? Well, this is a good question. We know that the spring is pre-compressed, so it has experienced a pre-compressed displacement Z naught, and when the piston moves further to the right, an additional displacement delta Z is over here. So the sum of the two is going to be the net displacement of the spring left terminal. So the force, if taken in acting on this terminal Fs, is shown here, then the expression is Fs is equal to K times delta Z plus Z naught. So in this case, the spring force expression contains the pre-compressed displacement Z naught. So this is the new component of the spring force. All right, as before, we now want to express the feedback displacement variable delta Y in terms of delta U and delta Z, or the linear sum of the two input-output displacement variables. So as a homework exercise, we're going to utilize the same tool, that is to overlay the final pose, that is making some angle with respect to its initial pose, a perfectly straight line. And in this case, the displacement are such that the input displacement is represented by a leftward vector, and the delta Y is in the rightward, so is the output. So as a homework exercise, you're required to show that you can split this figure as a sum of two geometrical figures, as was the case in the previous example, and delta Y can be written as A prime delta Z minus B times delta U. That is where A prime is A over A plus B and B prime is B over A plus B, same as before, and delta Y can then be expressed as A prime delta Z minus 1 minus A prime delta U. That's because 1 minus A prime is just equal to B prime. You can see that easily. So that is going to be our fourth equation. If we make a list of all the equations that we have developed so far for the pneumatic position servo, the first equation describes the pressure difference, the fluid pressure difference across the piston cylinder with the input pressure supply and the pressure drop, that is this term R naught Q naught, and the input pressure supply delta PS, and there is some pressure loss due to this nozzle, and the distance and that pressure drop is essentially regulated by this displacement delta Y that amounts to this the distance between the nozzle and the flapper. And then we also have the capacitance equation in which we made a couple of approximations by relating the time varying quantities, volume and the bulk modulus, approximating them to their mean values, V static and B static. And we also wrote V dot in terms of A times delta Z dot. And the third equation and the fourth equation for the mechanical subsystem, 3 and 4. And then combining all these equations, we are going to the final expression that relates delta Z with the input delta U and the other input FL. The expression in this case is a bit complicated. It is going to give you a third order system because you have this d to the power 3, not d so d to the power 3 indicates a third order system. So that that's because this is a pneumatic system in which this term doesn't cancel out. So it bears some similarity to the expression we derived for the hydromechanical position servo, but in that case this term was equal to 0. It's actually non-zero over here, but the system is still not linear though. That's because we have a constant term in the numerator that is not acceptable. So we need to eliminate this constant term that is delta ZSS. What is that? It contains the input pressure supply area times 0.671 times kz naught over ks. So one thing that is problematic over here is this term being non-zero, but if we want the system, if we want to develop the transfer function of a system that is linear, then this whole term must go to 0. This is it. Set delta ZSS equals to 0, and we can write down the equivalent requirement by when you set delta ZSS equal to 0, then that relationship between the input pressure supply and the pre-compressed spring displacement, that is Z naught. So we can drive a relationship between the two quantities by setting delta ZSS equals to 0 to give to come up with a linearized version of the system. So with that, I would like to formally conclude our lecture on the fluid power actuator systems. Hopefully you enjoyed this lecture, and I'm sure you will have some questions. For that, we're going to have our regular Q&A session on Thursday at 2 p.m. So till then, stay safe and take care of yourself. Thank you.